Hello everyone, my name is Ali, Ali Shayiq, my full name, and based in UCD, University College Dublin. So due to the time constraints, I will start my presentation. Well, my research is on the computational techniques for improving wire forming. The first problem when it comes to me introducing my project is that whenever I say wire, people think of these wires, while I'm talking about these wires. So the wires in on the sphere of manufacturing refers to a thin structure, but it is thin only compared to the length. So it can be 1 centimeter or 2 centimeter wide while it is 2 kilometers long. So in this scenario, it is still called wire. In terms of application, so for example, look at wipers. You can see the trace of the wire among the rubber in the wiper. These are the actually wires that are used there. And this is a spool of the same wire, a 2000 kg spool of the same wire. Another example, wire, again a copper wire this time, used in the generators, whether in coupling with wind turbines or other turbines. So yeah, just to refer that the industry partner of our research is Baker, a world-leading industry in wire forming, based in Belgium. I had a chance to be there last month, and actually my takeaway was a lot of industrial insights. And now this is the hard part, because we have a video and I doubt if it plays. So I don't see my pointer anyway. Where is it?
Yeah. It's been there for a brief period of time. If the presentation is in PDF, the videos do not work.
No, it is not. It is actually.
PowerPoint.
Yeah, it is.
So you want to play this video, right?
Yeah.
Okay. Well, let's show that this video cannot work.
Okay, so apparently, actually, I just made my presentation on online office, and then when we download it, apparently videos do not get downloaded. So the first step in wire forming is drawing. What happens is that the wire is drawn inside a drawing die. The diameter reduces, but one of the main purposes of drawing is to remove any non-uniformity of the diameter in the peripheral direction. After drawing, we have rolling, very nice videos which we cannot play here, but we have images, thankfully. So where are the images, I wonder? Yeah, actually I see the images here. I don't know what happened actually. So maybe we have a chance to see the videos very fast. That's drawing. And then we have rolling. So the idea is to change the cross-section of a round wire to the favorite shape based on the application we have in mind. So after drawing, the main pass, which is rolling, happens. This is a rolling stand with 4 rolls, another one with 4 rolls, and this one has 2 rolls. In the image, we clearly see that a round wire comes in, maybe mostly or 90% of the times the output of the drawing die comes to the rolling stand, and then it shapes to in this case a flat wire. So as we saw in the video, the number of rolls are not necessarily 2, they can be 4 or more. And the contact between the roll and the wire is not necessarily flat. It can have such a strange shape, or this shape. And if I complete this puzzle, I will end up with this product. So just to refer for your reference, the application of this profile is in making the wall of the oil transportation lines in offshore oil production fields, but it is also of a high importance for the next generation fuels, which is hydrogen transportation. So the few number of manufacturers of this profile are actually competing hard to remove any problem in the process of design and manufacturing of this profile and similar profiles. What are those bottlenecks for those manufacturers? First, the customer demands for a very tight geometrical tolerance, and every now and again, the designers at the customer's company come up with new profiles, so they are not always constant shapes. And every hour that the production line is overhauled, you have approximately 5 tons. You actually fall behind on your production goals by 5 tons, which is too much. So the solution is simulation, the potential solution. So that's why Baker and University College Dublin had an agreement a couple of years ago, maybe 8 years ago, to develop a tool for removing the current bottlenecks in the design process. So I straight away go to the model that we have used. We have used the Lagrangian description for a material body, which is wire in our case. We reformulated to updated Lagrangian formulation. So it is Lagrangian because the domain of integration is a material body, and it is updated because we describe the motion in terms of the reference configuration. And in our case, the reference configuration is the last known time step. So just the constitutive relation is in terms of the Kirchhoff stress. The algorithm, well, simply you need to discretize the domain first, closer look, and then you end up with, sorry, maybe I need to wait 3 seconds. Normally it takes just 3 seconds. So if you don't want to wait, we can see the video here. You end up with such simulation by solving those equations on that domain. One challenge in this Lagrangian simulation is that you don't know how long the initial piece of wire should be so that the simulation reaches the steady state, because that's the goal of the simulation. So we actually, Tian Tang, some years ago, came up with a solution which was solving the equations that are shown for one time step. So basically we move the wire and then we return the wire, we impose 2 conditions on the upstream and the downstream. So we shrink the very end cell and we extend the very first cell, so that as if the wire has not moved at all. And then we map the domains from the top, which is the solution, to the bottom. But we end up with such a scenario where we have very sliver cells, very large cells at the beginning and very small cells at the end. So what we do at this point is that we remove the last cell and we split the first cell like this. So, and we end up with a high quality mesh again. And we do this every time step until we reach steady state. The figure on the left shows the implemented version of the right one, the modified version of the right one. So we first you need to verify this implementation. We did so across against Abacus. Qualitatively, they show good. Just as a quantitative comparison, we see that time to, so in this graph, we use equivalent plastic strain as a measure for steady state. So we see that both reach the same steady state scenario, although, well, in this specific case, OpenFOAM has reached, OpenFOAM is in violet color, and you see that it has reached the steady state a bit faster. A bit more about the functionalities of the tool. Well, complex profiles like this is quite capable of running, actually executing and obtaining different profiles. However, there are some practical issues. Maybe I skip this slide. When the deformation is so severe, the simulation crashes. Also, there are other, I mean, from the technical point of view, there are other problems with this current simulation tool as well, like the prediction of elastic spring back and work hardening. When you deform a material, it becomes harder. We need to implement those effects in our method as well. But at the moment, we focus on severe deformation, which is the simulation stops when you want to produce such a profile. So you can see that how it will be how difficult it would be when it comes to reshaping the initial configuration to a shape with sharp corners. I have less than 3 minutes left. That's it. So the way actually the method we came up with was remeshing. However, remeshing, so which means that when the simulation stops due to severe deformation, you remesh the domain and rerun the simulation. However, our remeshing at the moment is actually unstructured. So it is just, I'm trying to show that this last cell is remeshed on a structure in an unstructured way. You can spot that now the layer addition removal that I mentioned cannot work anymore because you don't have any layers at the end. So there is no layers to be removed. So the whole idea of the having a fixed piece of wire collapses unless you come up with some idea to be able to use that method again. So the algorithm we came up with was starting the simulation, remeshing when the simulation crashes, and then removing the part of the wire, removing a piece of the wire at the end. I will show in the next slide. So maybe I can explain on these pictures. Assume that this is the distorted mesh, and you do the remeshing. So before doing the remeshing, you want after remeshing, you want your mesh to be layered after remeshing. You want your mesh to be layered at least at the last cell on the downstream. So you remove an arbitrary part of your wire at the downstream, you remesh, and you end up with a very organized cell, a very uniform cell, and then you extrude the mesh again to the extent that your downstream was, and now you have layered mesh at the piece that you need layered mesh. We tried it for the pierced knot case that I showed here. This was the pierced knot that is our main challenge in this case. We tried this method on this case, and so without remeshing, the simulation crashes before we reach steady state. We added remeshing, and we still have not reached steady state. However, it was a great success for us that we could progress too many time steps further. And this is this is also another comparison between the forces, roller forces for both remeshed and non-remeshed cases, just to show that it doesn't introduce an error to our work. The next area we want to explore is arbitrary Lagrangian Eulerian, and hopefully it will help us to sort out the problem efficiently. And I would like to acknowledge our financial supporters, Science Foundation Ireland, Baker, University College Dublin, and I4. Thank you so much.
Okay, thank you for a very interesting presentation. Please, do we have any questions from the audience? Okay, if not, I have one, and it's basically, why do you use updated Lagrangians when Lagrangian formulation, when you have all these problems with remeshing? Why not to use total Lagrangian and couple it with finite deformation framework?
Well, actually, if I remember correctly, there was, I mean, in terms of physics and equations, there seemed to be no difference between the two. However, in terms of implementation, there is an error. I can actually there is a paper in which Philip Cardiff, the developer of the original developer of the software, has published in 2016, and he mentions why we don't use total instead of Lagrangian. As far as I remember, it had something to do with reconstructing the gradient terms. For in total Lagrangian, it was much less accurate than the updated one. But I can check the paper and let you know afterwards.
Okay, thank you.
Thank you.
Yeah.
Thank you. A very good talk. You said your simulation have the remeshing process. So I want to know how is your computational efficiency in your simulation?
Well, for example, for the flat wire case, which is kind of the simplest possible scenario, for one rolling pass, it takes 40 minutes to reach steady state. However, as you know, it completely depends on your mesh density and how long you have chosen your first, the first piece of wire. But remeshing doesn't introduce any recognizable time, computational time. Yeah.
Okay, thank you.
Thank you.
Okay, so let's thank the speaker again. And
thanks so much.